let's address the same example, but with rescaling technique. So as you remember, we introduced the new integration variable s, which was related to the previous one according to the following relation. And what we notice is that there might be some problems as we change the sign of x from positive to negative values. So let's first address the issue of how we could actually change the sign of x. So this is our real axis, which denotes our x. And we seek for asymptotics at large positive at large negative x. So the first tempting change would be just the smooth change along the real axis from large positive x to negative x. But as we make a change, we cross the point x equals to 0, which is obviously the singular point in our change of variables. So let's try to avoid it. And probably the best way is to change x in such a way that, first of all, its modulus remain large, and it doesn't cross this singularity, the origin. So let's actually change it in the complex plane. And for definiteness, let it be the upper complex semiplane. So we rotate our x as follows, where its argument interpolates between 0 and pi. Also suppose the initial position of the contour, the real axis, is fixed. So the t. So t belongs to the real axis from -infinity to +infinity. So what's going to happen with the s variable? So s will change also accordingly. So s is t divided by x. So the argument of t is always 0. So that now we understand what's going to happen with the argument of our s complex variable. So we change x to modulus x to e to I phi, so minus I phi in the denominator, and we see what's going to happen. This is our initial position of the contour for positive x. Now x starts rotating, and with this start the rotation. The s complex variable, and as you see, it rotates in the negative direction, so it's clockwise direction, like this. With this, in a quite synchronic way, rotates the position of the pole, because the position of the pole is given by -I over x. And as a result, it also rotates by phi angle in the clockwise direction. So this is the initial position of the pole. This is how it rotates. So as we make the full rotation by pi, then our contour in a complex plane of the complex variable s also rotates by pi. And the final position of the contour would be here, of the pole would be here, and the position of the contour will return to the real axis of s, but the limits of the integration will change. Initially, the limit stretches from -infinity to +infinity, and after the rotation, it will change from +infinity to -infinity. So that's the difference, the subtlety when you perform that kind of rescaling with a scale which can potentially change the sign. So now we understand that the correct representation of our initial integral is that contains additional sine function in front of our integral. So far, so good. And now let's start again. Let's explore the asymptotics of the integral for large positive and negative x. First, let's study large and positive x. So now our exponent function is homogeneous. Our large parameter is simply s squared. So let's locate the saddle. Now the position of the saddle is independent of the sign of x. So it's simply I. The steepest descent direction, as before, defined by the argument of the second derivative, which is pi. So the steepest descent direction, unsurprisingly, is again a horizontal line. And if x is positive, then the pole is positioned below the contour, and nothing prevents us from the parallel transport of the contour by by 1 into the complex plane, so it passes through the saddle. And next, we expand our pre-exponential function. So in the vicinity of the saddle, was s is equal to I, one can safely drop I over x term. So it's simply 1 over I. And indeed, because due to the largeness of this parameter in the exponential, the important regions of the integration is s of the order of, as you remember, 1 over square root of lambda. So s is of the order of 1 over lambda, where s is the complex variable counted from this saddle. So the important region is just a small disk of radius 1 over square root of lambda, 1 over x. And indeed, that gives us the reason to drop this 1 over x term altogether. And now the integral is again reduced to standard Gaussian, and we can actually use the standard formula for the saddle point approximation, which is square root of 2 pi by lambda, and lambda is x squared, times the value of the pre-exponential function at near the saddle, 1 over I, times the value of the function at the saddle, to just plug in s is equal to I into the exponential, and you get minus x squared over 2. The steepest descent direction angle is 0, so there is no additional argument here. So, and that's it. That's the correct asymptotic. So it's square root of 2 pi divided by ix times the exponential. So it's just as before, as the same asymptotic that we gained from the technique without rescaling. Now, we discuss the case of large and negative values of x. This time, the whole contour, as you remember, rotates. And here we have a pole in the upper complex plane. So when we try to deform the contour so it passes through the saddle, we again move it upward, but the deformation hooks up the pole. And in complete analogy with the non-rescaling technique, the correct deformation of the contour would be again the stationary phase horizontal line, the stationary phase vertical line which connects the saddle and the pole, a small circle around the pole, this time in a counterclockwise direction. Again, the vertical leg connecting the pole and the saddle, and gliding along the steepest descent direction from the pole. And finally, the second horizontal leg, which glides along the steepest descent direction from the saddle. As before, the vertical legs of the contour cancel because all the functions are single valued here. There are no branch cuts. And the integral is split into the contribution from the pole and the contribution from the stationary phase line gliding through the saddle. Let's first compute the contribution which comes from the saddle. Let's keep in mind that now there is a negative sign of x, so -1, due to the negativeness of x in front of the integral. And the rest of the contribution just stays exactly the same. So it's square root of 2 pi. But now, some subtlety here. As we make a square root of this x squared, we get, of course, the modulus of x, right? Because in the standard formula, probably you remember, there is a modulus of f prime prime here. So there should be a positive expression under the square root. So it's modulus x. And finally, 1 over I e2 minus x squared over 2. But minus modulus x is simply x for negative x. So the contribution from the saddle stays the same. And now the contribution from the pole. Again, it's a simple pole, and the contribution from a simple pole is simply, so here the direction is positive, counterclockwise. So it's 2 pi I times the residue of the function. Okay, let's keep in mind this negative sign in front of our integral. So it's not 2 pi I, but minus 2 pi I. And here we go. So s is equal to minus I over x. We just compute the residue. And as before, we arrive at the expected expression. It's x plus 1/2. And this completes our discussion. So as you see, we obtained completely identical answers for the integral in the technique with rescaling and factorization of our exponent function. So both methods worked perfectly well and yield identical answers. So hopefully you got the main point of this discussion and use both techniques at your will. Thank you.